Hi everyone, welcome to my undergrad presentation for Fundamentals of Deep Learning. The paper I'm going to be discussing today is titled Incremental Few-Shot Learning via Implanting and Consolidating, and this was published in Neurocomputing in late 2023. So for some background on some related deep learning tasks, we have incremental learning, and this involves learning new knowledge over time without forgetting previous knowledge. And in classification tasks, this would mean learning how to classify new or novel classes while retaining the ability to classify previously learned classes. So in this example here, we have a model that is able to classify between airplanes and automobiles. And then we also add the ability to classify birds and dogs while still being able to classify airplanes and automobiles. And we also have few shot learning, which is learning new knowledge while given only a few samples. So in order to do this, models are pre-trained on large data sets, and that helps them learn generalizable features that they would then use for distinguishing between novel classes. So you can see here we have three classes that we want the model to learn to classify while given only three samples for training. We also have incremental few-shot learning, which is the combination of these two tasks. So models must be able to learn new knowledge from only a few samples while maintaining previous knowledge. And this is what the paper is focused on. So some of the challenges that we run into with this task is catastrophic forgetting. This is when the model loses the ability to classify older classes since that data it used for training was no longer available. We also have being able to learn generalizable features during pre-training, since some novel classes might have unique features. We also might run into class level overfitting, where the model might overfit to some classes, like base classes, and this results in worse performance for the novel classes. We also have interclass separation, which is the space between classes in feature space. So we want more space between them to avoid classification errors. We also have problems with intra-class separation, which is the space within one class in feature space. And we want this to be compact since we're only given a few samples. So those few samples might skew this separation. Some previous approaches that we've seen to IFSL are forward compatible training, or FACT, and what this did is reserved space for future classes by mixing in synthetic data, and this effectively increased interclass separation. But one of the shortcomings was that it froze feature layer parameters after the pre-training stage, and this meant that those parameters couldn't be updated to better classify novel classes, although the point of this was to prevent catastrophic forgetting. We also have the finding flat minima technique, and what this did is it found flat local minima during base class training, and then during the training on novel classes, those parameters could be fine-tuned, but they had to stay within that flat area. So this paper introduces a new approach called implanting and consolidating, or IMCO, and this effectively combines some of the ideas from those previous papers. So first we have the implanting stage, where we mix in synthetic data, and we also have the consolidating or compressing stage, where we fine-tune our feature layer parameters. So in order to implement implanting, we mix the feature space vectors of real points of data from two base classes, and then we introduce them during pre-training. And this relies on the fact that novel classes will often have features that are in between other classes. So by implanting, we are making space in feature space for those novel classes eventually. In the consolidating stage, we are fine-tuning our feature parameters, and in order to get around the catastrophic forgetting issue, we regularize this parameter updating in a few ways. First, we evaluate our parameters for their importance and classifications. So important parameters are constrained, while unimportant ones are allowed to update to better classify novel classes. And we also use dense model fusion to reintegrate old knowledge and prevent forgetting. So this IMCO method and other IFSL methods were evaluated by applying them to the ResNet 34 architecture, and then training them on several image datasets. And these image datasets were split into base classes for pre-training, and then the leftover novel classes were introduced to the models over 8 sessions. and then the accuracy was assessed at each session. And IMCO was also tested when combined with the finding flat minima technique. And here's a picture of the ResNet 34 architecture, and we can see the stages where implanting and consolidating were implemented. So for the results here, you can see in the red text is the method that had the highest accuracy for that session, and in the blue is the second highest. We can see IMCO plus F2M had the highest accuracy, at least in the later sessions, for both of these datasets, and also in the ImageNet datasets. So some things that we can conclude from these results. First is that synthetic data implanting does appear to be a legitimate method for improving accuracy. And we could see that in the high accuracy for FACT and IMCO, at least in the mini ImageNet dataset. We also see that we are able to fine-tune our feature extraction parameters without running into catastrophic forgetting. And we also found that combining IMCO with the F2M method resulted in the highest accuracy across all datasets consistently. And in this figure here, you can see the effect of implanting on the feature space separation between some of the novel classes. So without implanting, there doesn't seem to be much interclass separation, but with implanting, it's clearly visible. That's it. Thank you.